Welcome to Wasm. What is universal compute good for? My name is Sean Isom. I'm a senior engineering manager at Adobe. I work on our cloud compute platform. And as Colin mentioned, I live 3 blocks that way. You can see this from my apartment, so long commute for me this morning. Today we're going to talk a little bit about WebAssembly, a little bit about Edge, a little bit about cloud architecture, and I hope you can take away from this talk how and why you can use WebAssembly to build a universal compute engine that allows you to bring your code closer to your data, increasing your efficiency, increasing your application's performance. Let's go ahead and dive right in. Okay, so what specifically do I mean by universal compute? Imagine a world where you can ship your code to any device and run the code where it makes the most sense. Sounds great, right? This might sound familiar. People have tried different techniques for this before through various virtual machine technologies, IDLs, bytecode formats. One example that comes to mind for me specifically is some of the early days of Java, which I'm sure is something that a lot of people here can empathize with. One of the early design goals of Java was to be able to have a portable bytecode format can run on a plethora of devices, abstracting away some of that underlying hardware, allowing developers to focus more on the business logic that matters to them than the underlying infrastructure and the underlying host. So I would call WebAssembly kind of the next generation of this. It is simply a more modern tool that's going to allow us to run that code not only on any device, not only on any form factor, but where it makes the most business sense to the actual application in question. Because that's where you actually derive value from these kinds of large architectural shifts. Let's establish a thesis statement. And actually, first I always like to start my talks with a quote, and this is a good one. Compute is nimble and can be easily moved anywhere. Data is heavy and moving it has a cost. This is from an individual named Glauber Costa and actually comes from an article on the New Stack called What the Heck is Edge and Why Should You Care? It's a really great write-up. I highly encourage you to go read it and learn a little bit more about why people want to move code to the edge in the first place. But let's apply this to establish our thesis statement. And that is this. WebAssembly is the best tool for universal compute, but moving compute only makes sense when you improve data locality, when you improve performance or cost, when you move some sort of metric and move the needle in a positive direction. When you improve your data locality, you drive more efficient cloud-native architectures in the first place. My goal really is to convince you that, yes, we can run the universal compute runtimes anywhere, but that there's heuristics and frameworks and techniques we can use to think about where that code should run, both at runtime and at design time. Some may argue with the fact that compute is actually that nimble. Let's say you're building something around a specific cloud provider SDK. You're running an AWS Lambda function. You need to pull data from S3. You're probably using the AWS SDK for whatever language you're running in. You're locked into that framework and you're locked in that way of doing things. But rewriting that chunk of code that's more generically pulling data from some sort of blob store is still easier and cheaper than, let's say, running a Lambda and pulling from a different cloud provider, or pulling from a proprietary piece of block storage. So that data component is critical to understanding where your application should run, because really your application is just a set of code plus data. So compute is fairly nimble, I would say nimble asterisk, nimble if we design it from the outset to be nimble, nimble if we design it to be moved around, but we want to move it on the basis of where our data resides and where that data is going to be closest to the user and the use case necessary to operate on that data. So today we're going to talk a little bit more about universal compute and some of the background on WebAssembly, how Adobe uses WebAssembly, both on the back end and on the front end. A little bit about how one should think about architecting for edge and architecting for moving compute across different devices. Some of the value prop of building code for WebAssembly in the first place. I'm going to go through 3 different architectural examples where WebAssembly can power this concept of universal compute, allowing you to move that around. And then end on a discussion of scheduling, or where should the code run. I think there's a lot of useful heuristics you can apply at design time and at runtime, but you can also algorithmically schedule based off of some sort of measured metric. So this is a bit of a fascinating proposition, this concept of universal compute. And I want to start with a bit of a background on WebAssembly. Well, I wanted to start with the background on WebAssembly. It seems like everyone raised their hand here and has heard of WebAssembly already, but I'll still give the background in case you just know some of the basic definitions of it. So WebAssembly provides a universal runtime. It's a universal bytecode format. There's a set of associated tools and runtimes like Wasm time, which is one of the more popular ones backed by the Bytecode Alliance. But WebAssembly is a set of standards and set of technologies that allows you to write your code once and run it anywhere. I love this quote, and I think it's attributable to Tyler McMullen, who's the CTO of Fastly, who've been some of the pioneers in the WebAssembly space. But let's discuss the evolution of this over time. WebAssembly started in a web browser. That's why it has the name WebAssembly. And a lot of the motivation for doing this was being able to run native code, run high-performance code in a sandboxed way within the context of a web browser. So you're bringing that core compute and that business logic to a new form factor to solve some sort of business problem, to increase your number of channels you have to sell software to your users, to be able to integrate in with more modern stacks, web-based UI frameworks, for example. It allows a common code base to be able to work within the confines of a web browser in a fairly standardized way that is both sandbox, isolated, but can also efficiently communicate with the host system itself. And here in the example for a web browser, the host system is kind of twofold. The host system is the web browser, but there are also underlying system processes as well. There's underlying compute capabilities that live outside of that web browser that are necessary. And so over time, people started looking at WebAssembly holistically and said, is this something that can run outside of the web browser? There's a well-defined set of standards for sandboxed, highly performant bytecode systems that can be AOT compiled for native hardware. So you can imagine a flurry of use cases start springing up around running this outside of a browser. Maybe plugin systems for a game, maybe some sort of dynamic application, some sort of function as a service, a method to write very specific chunks of sandbox code and run them in a safe, performant way. So all of these outside of the browser use cases start appearing, and things like the Bytecode Alliance and WASI, or the WebAssembly System Interface, spun up to allow WebAssembly to work well outside of a web browser. And this is really interesting. So we've got web, we've got desktop. Two different worlds, right? Well, maybe not. Maybe the way we should be thinking about this is it's still the same WebAssembly, it's still the same code. It's still the same guarantees, and it's the same application model that we've written for this more generic computer. Let's call it that. It's a generic compute runtime. But it's running in a plethora of different form factors. That same code, independent of system resources, and can run in both of those locations. And so we've got two. Let's think of more. What about IoT devices? At the end of the day, these can be viewed kind of like a desktop computer, just a much more constrained compute environment. And with the performance of WebAssembly, with the safety of WebAssembly, why not run that same code that's running in your web browser, I don't know, on your refrigerator, on your toaster? Joking about that one. But in all seriousness, there are the same guarantees across these different form factors. Performance, security, being able to run that same chunk of code in a more constrained form factor, be that a browser, be that a desktop, maybe a server, and that extends to edge compute as well. When we think about edge compute, often there's a lot of different definitions, but we associate this most with things like telcos, different edge cloud providers that are not centralized, but maybe provide some sort of resource that's still multi-tenant, still programmable, and closer to the user than a centralized cloud region or data center, although maybe not quite as far out as an endpoint device like some of these other three. Why not bring that same chunk of code that's running in a web browser? Why not run that same function on a desktop? Why not run that same function on your toaster? Why not run that same function on an edge device? There's no reason you can't. And so you can also bring this to the cloud. And this is kind of where we come full circle with traditional architecture between a client and a server, a client and a cloud. there's a lot of different architectures for what we call cloud and a lot of different ways to define cloud. But through things like AKS Wasm node pool support and a lot of the PaaS platforms that have sprung up over the last year, there's really easy and straightforward and performant ways to run WebAssembly within the cloud as well. So this is where this concept of write once, run anywhere in universal compute becomes really cool. I don't have to write WebAssembly for this one specific thing, this one specific use case, or this specific device. I think the concept really shines by being able to abstract the system, abstract the host, abstract the language, and be able to run the same core business logic across form factors where it makes the most business sense. And that's because WebAssembly is simply a lot more than just the runtime itself. It's the developer ecosystem. It's the mechanism we use to communicate across components. It's the mechanism to access that data in a standardized way, separating it from the compute to be able to manage those dependencies. If you're running on the cloud, on the right, for example, you're probably modifying multiple containers. You multiply that across all of your different applications, all of your clusters. Let's use the log4j vulnerability as an example. Anybody remember that from a few years ago? So you've got to rebuild all those containers. You've got to ship those sets of containers across all of your environments and all of your clusters. Well, maybe we should invert that model a bit and start thinking about dependencies in terms of capabilities. And that's what allows us to have a better developer experience, where we can just update the code and the manifest in one place and let the runtime itself take care of patching those libraries when they're abstracted away from the business logic. So that's why I think WebAssembly is really turning out to be a much beefier, much stronger technology that allows us to not only run in multiple places, but support the ecosystem and the data for an application in multiple places. So specifically this talk, we're going to focus a little bit more from these boxes on the interaction between edge compute, cloud compute, and client hardware, and how they can interact with the same WebAssembly modules. Let's give some preliminary background. Adobe has run WebAssembly successfully for many years now. And actually, taking a step back, looking at some of the predecessors, some of the previous attempts, things like Isom.js, and actually, has anybody heard of Google's portable native client? Yeah. So these are some early attempts at running sandbox question mark, running safe native code in a web browser. And the reason we want to do that is because we can reuse some of these native code bases that a lot of large companies have that have many decades of investment. This is kind of led and bled across different products. It started with Lightroom Web. I think that actually originally launched on Isom.js, and with our more modern web stack, products like Acrobat.js and the actual Photoshop beta, which is in a web browser, mostly using the same common code. There's a lot of integration into UI frameworks, so WebAssembly is becoming the default. And you see that in some of our next generation products like Firefly. This is a recently announced beta, which is a generative AI engine, which is a very hot topic for many organizations today. So as we've adopted WebAssembly, it's kind of gotten to the point where it's powered a lot of our front-end products. And the reason behind that is because it meets all those guarantees that we talked about. It's a high-performance system. We can utilize those existing code bases, and it's secure by default in a multi-tenant environment like a web browser. Speaking of multi-tenant environments, obviously there's backing services behind those products as well. Adobe runs Kubernetes. As the complexity of our user-facing products grow, the size of the back-end capabilities grow as well. I'm sure this is something most people in this room are interfacing with. It seems like there's very few organizations today that are not running Kubernetes. This is not an exhaustive list of everything that's running in what I would call our cloud, but you can imagine that centralized Kubernetes and container infrastructure powers most of our capabilities. We've got over 5,000 production microservices, 5.5 million different running containers. So no matter how you look at the metrics, we run a lot of compute on the back end to power those front end products. So you can imagine how we have a very high performance end user product, very high performance back end that's powering those products, but what sits between? And this is where the concept of the edge comes into play. Now, I promise you this is not just an edge talk, right? We're here to talk about WebAssembly, But I think we have to give some definitions of this and talk about what lies between back end and front end in terms of being able to shift compute around. Remember that original quote, what the heck is edge and why does it matter? I love using this graphic to explain. This is from our friends at Cosmonic. Thank you very much. I think edge means a lot of different things to a lot of different people. To me, edge is a good form factor for shifting compute and allowing us to have better data locality. And so by edge specific to this talk, I mean things in this graphic like the regional or access edge. These are systems that are outside of maybe the major cloud providers, outside of corporate data centers. They're run outside of centralized locations. These are compute nodes that are just out further towards user endpoint devices. There's other definitions as well. Like some might actually consider a web browser to be an edge device. And that's fine. That's maybe an extreme example of as a company, you're not paying anything for that compute, and you are paying something for the data to get that WebAssembly module to the user, but the runtime cost is from a financial perspective essentially free. Anyways, there's no right or wrong answer on this, right? This is intended to say this is a spectrum. But for this talk, we will define edge to be sets of services that live between centralized data centers and that endpoint user device. There's a lot of different architectures, a lot of different ways this can play out for different organizations. And then let's dig in on service architecture as well. What might a typical web service look like that's running on that back end? And what are some of the different capabilities it's doing? And what are some of the functions that we can use maybe to offset some of this compute on the back end? First of all, services come in all shapes and sizes. Speaking to a room of developers and architects, so this should be no surprise. But within our multi-tenant platform, you can graph kind of a services utilization and resource and capacity requirements like this. These are 5 dimensions that matter to us. There can be different dimensions that matter to different applications. But essentially, you are mapping some sort of system capability, in this case, CPU, memory, network, disk throughput, and IOPS. You're mapping some sort of fixed capability to a more dynamic client runtime that's not going to fill all of that. And that's okay, right? If you were to 100% utilize your CPU, your accountants would probably be very happy. But then your application would probably have huge QoS problems. And at the end of the day, that's not a good thing. If you fully utilize your memory, it's probably crashing and restarting. If your disk is full, it probably can't do much else. And so if you were to graph a bunch of different applications across here, what you note is the shape of that yellow line in the middle, that shape of that utilization graph is going to be all over the map. And that's kind of the blessing and the curse of multi-tenant systems is you have to play Tetris a bit, you have to bin pack, you have to fit, you have to utilize those backing resources effectively to match the requirements of the application itself. But let's dig in on how this specific service site graph, what the service doesn't matter. I just want to use this as an example for the rest of the talk. So by default, it's Java and Spring Boot. It's running in Kubernetes in a containerized environment. It's going to be running at about 28% CPU utilization, 55% RAM utilization. It's going to have a pretty large RAM working set because of how Java allocates the heap in a container. It's going to have a workflow that looks something like this. It's going to be running some sort of thread pools that you can fork a thread, or not fork, you can take a thread off the thread pool and be able to handle some sort of incoming web request. It's probably a REST API request that's coming in from a front-end product. Might be coming in from another service, and you might have a chain of services calling each other. There's a lot of different answers to this, pretty typical pattern. You're going to take that input from the REST API, you're going to transform it in some way. You're going to perform some sort of data operation on that input. You're going to go out and request data from some sort of dependency. Could be a database, could be block storage, doesn't really matter what the dependency is, right? There's very few services that take data in, crunch a number, and spit something out without talking to some sort of dependency. And it's going to send that response. And it's going to send that response synchronously back to the user, but probably also asynchronously back to another set of services. Maybe you've got an eventually consistent system. You need to update some sort of system of record. This is not supposed to be an exhaustive example, but the idea is just start thinking about if I've got a bunch of containers on the back end, they're serving front-end products, that look like this. What can I do to run those in different environments? And so let's think about how we can architect for edge and how we can discuss cloud architecture in terms of boxes. I like boxes. I'm a pretty visual person. A lot of architecture is two boxes these days. You've got a client and you've got a server and a data center in this nomenclature. And your users just want to do a thing. They don't really care about the architecture behind the product that they're using. Let's say they hit a button in your product and they want it to go perform an operation. So there's already some decision points at runtime for the product or done by you as the developer as to how to power that request. For example, on an endpoint user device, you have to think critically about, can I quickly run this functionality? Like let's say I'm running some massive ML model. I'm running a generative AI model. Like I said, all the hype these days. I probably don't want to pull down that entire model, load all of the weights into my local VRAM, spin it up, do the inferencing locally, and use that result in another function. That's very wasteful, very silly. Also probably an extreme example. But for a constrained compute environment, you might want to answer this question a little bit differently than in a desktop environment where you have a GPU. And if you need to perform some sort of convolution-based process, you have a very powerful parallel processing mechanism to do that. Maybe on a mobile device with 5% of your battery remaining, you want to call out to some sort of web service to perform that same operation instead. The other decision point is kind of around data locality. Does this device have the data locally to do the thing? Let's use the example of an order history system. Every single order is probably stored in some sort of database somewhere on a server. And that makes sense because the actual payment gateway lives on that server. And so does the user device need the entire order history for the operation? Let's say that the function you're accessing, the user doing a thing, is trying to view their shipment status on their most recent order. You probably don't need that entire order history in local cache. Maybe you could cache something more recent closer to the user. There's plenty of other real-world examples. These are just some of these decision points that when you're writing client-side code, you have to make. Where edge becomes really powerful is thinking about a closer method to run offline compute to a user than a data center itself. Are there existing compute functions that can be split off from a client application? Does it make more sense to run in a more powerful environment, utilizing the network, injecting latency, but still while keeping that compute as close to the user as possible? Is there a way to split off functions on the other side from the back end? Maybe we don't need all that round trip latency. Something's running on the back end. If we have a device that's capable enough using the WebAssembly model to run that compute closer to the user. So going back to the order history example, if you have to pull the full order history every time for your operation, edge makes no sense because then you're going from client to edge, your cache is cold, you're going to the server, pulling from the database, going back out, etc. Right? There's no point to caching everything. That's wasteful. But if you can summarize that user profile, or if a subset of the data makes sense to keep warm, you can not only reduce the cost, but you can move that data one time and improve the performance and the user experience. And then last preliminary slide, before we get into more specifics. I don't want to spend long on this, but I do want to talk about how to run WebAssembly inside Kubernetes. This is a graphic from a talk I did at KubeCon EU this year. You can go watch the talk if you want more technical details on this. But for the sake of this talk, I want to make it clear that you can easily run WebAssembly code for your service in Kubernetes. And that's what's going to allow us to shift that compute between the client side, edge device, and also in Kubernetes on the back end. This is a method that we have set up to do this based off of Wasm Cloud. There's other ways to do this. There's no universal solution. Basic idea is to utilize providers within the context of an existing Kubernetes namespace. It's going to be one of those blue boxes on the right. And utilize something called the service supplier, which is going to create a Kubernetes service, provision ingress, essentially, for an HTTP request, hook that up to an HTTP provider. That's going to communicate via NATs outside of the client's namespace into a pool of common Wasm Cloud hosts. And these are the things that are actually running the actors or the functions that power the business logic. And then also you can communicate back out, right? If you need to send a result, or if you need to access part of that service's existing capabilities that are already provisioned in the namespace, you can bidirectionally communicate via the Lattice network back into the namespace for horizontal service communication, pulling data from dependencies, S3, et cetera. There's a few links on how to do this at the bottom as well. So taking the previous Java example, let's say we've got a large container that's doing things. We split off that function that's serving that request to more of a function as a service model. We've still got sidecars in the namespace. We're still running the compute the same way we were before, but we have the capability to centralize that compute runtime within that pool of common hosts. Like I said, not intended to go deep into this, but just want to say that there are ways to do this fairly easily to run this compute on a variety of form factors. The other important thing is not just running the code, but being able to manage the code's dependencies. And this is where WASI, or the WebAssembly System Interface, comes in. More specifically, WASI Cloud, which is a new set of standards that are coming out of some of the WASI working groups. There are things like WASI SQL that are coming out that will make this possible. I bet this is an example that resonates with a lot of people here. With most cloud architectures, I would say at this point, you're probably running some sort of SQL-based system somewhere. It's a very common capability. You need the ability to interface with some sort of backing store or KV functionality in order to introduce state into your code, into your logic. So we want to build upon the original foundations of WASI, which allowed us to have a system interface to safely expose host resources to a WebAssembly module. Like looking at some of the earlier work, like WASI Rando or WASI FS, we're kind of building off of those basic system capabilities, being able to access safely system resources, and we're leveling those up towards cloud-native architectures as well. Maybe you care less about programming for a specific database, like Postgres, right? You just need access to a stateful backing store. You've got some sort of shim, and you're programming for the WASI SQL interface, and you can plug that in, and it can work in a variety of these different environments independent of the backing provider. So the point I want to highlight here is just that this is what's going to allow Kubernetes to work across these different, did I just say Kubernetes? This is what's going to allow WebAssembly to operate across these different compute environments. Not just in terms of raw system capabilities like random numbers, these very coarse POSIX style system capabilities, but higher level cloud native capabilities or application level capabilities as well. Okay, we get to the good part now. Let's talk through some actual use cases. I think this will help people start thinking about why shifting compute makes sense. My colleague Colin Murphy gave this example at Wasm Day EU in 2022 of the background removal service. It's a very simple concept. You got an image here. In this case, it's a signature, and you remove the background of it. And that's it. I'm sure everyone in this room has probably utilized some sort of capability like this in some product at some point in their lives. This is traditionally for us a capability that's provided by a Java service that looks very much like the one I described earlier. So now if we were to go back and take the actual function that does the image processing, that does the background removal, takes the IO as input, transforms it, performs some sort of operations on it, sends the output back to the user for further use, let's say superposition on top of a PowerPoint slide. Let's build the code that does that function as a WebAssembly module in the first place. So the first step for that looks something kind of like this. Logical answer is, let's run this logic on the client side. We can do this in a web browser. We can do this within a desktop product using some sort of embedding engine for WebAssembly. There are also ways to do this on mobile. These are really cheap compute devices, thus the green box in terms of cloud spend. So maybe instead of running this back in a server-based environment, maybe instead of running a service for this, we run this on the client device itself, shifting that compute closer to where the data is, because the image itself is probably in some sort of local store, local cache. Well, maybe you're power constrained. Maybe you need online functionality for further processing. You can run the same code on the edge through things like Wasm Cloud or other edge provider specific implementations. You You don't need a full-featured server. A constrained compute environment will work, but it's less constrained than the free environment that's running on the mobile device, but maybe very low power. You've got pretty fast ingress, pretty cheap egress as well, lower latency than going back to the server-based environment. So you're still running pretty close to the user, but you've offloaded that compute. So you've exchanged that runtime cost for a network cost and associated network latency, which whether that's a bad thing or not for you really depends on the application, depends on the use case. There still might be some reason to run this in a data center as well, to run this within Kubernetes. You can run this as part of a native application, but the real power comes when you're able to run that same background removal function as a WebAssembly module within Kubernetes as well, using that same core common code base. The developer experience is great because you don't really care about where the code is running. And that takes us back to the very original points of the talk, right? That's one of the original design goals behind all of these systems, is being able to abstract away the underlying compute hardware. Why would we do this in the back end though? Well, maybe you need the transformed image for further operations. Maybe you synchronously need to update a document store because someone else is depending on that data. Maybe you're composing a stack of these single images into an ML model. There's all sorts of different use cases. So in that case, the data residency to the back end, to where those more powerful models live, is more important than the data residency locally, and therefore the network cost makes sense. There's no right or wrong answer to the question of where do I run this code, but WebAssembly allows us to choose the best place to run it and to have that universal compute engine based off the actual product use case. Let's go to a bit more of a complex example. I personally love this one, not only because it's code I wrote, but also because it introduces the concept of programmatic and decision-based scheduling. This is an example that I gave at Wasm.io earlier this year about how to use Wasm to optimize your data. So there's often large chunks of data that are generated through some sort of vector processing. In this case, we're going to use 3D models as an example. So you could replace the output 3D model with the set of instructions that are used to generate that 3D model in the first place. In this case, geometry operations. And you can represent those instructions through a formal grammar. So here's an example on the right. It's too small to actually read, but take my word for it. There's an example on the right. It's just a formal grammar that's been transpiled in C++, can be compiled down into a WebAssembly module that when you run the entry point of that function is going to actually generate the output. It's going to generate the data. This is super valuable because then you can shift from before where you might be streaming, let's say from some sort of centralized data center, a very large data set, you can shift that to the client device, or you can run that on the edge, or you can run that generation step at runtime, save some of that bandwidth for transferring what could be a huge binary object, and save some of that latency as well, while exchanging that for a runtime cost. It's almost the opposite of the previous example. So let's missed a few bullet points. Let's see what this looks like in practice. So on the client side, you've got a graphics engine that's hooked up to a GPU. Doesn't really matter which one. So it's going to determine that data is non-resident, and it's going to need to make a network call out to get that data. Why? I mean, we've all played video games where that is not necessary. You've got everything installed on your device locally. But think of a larger example. Think of something like a map. You couldn't store a high-resolution map of the entire world on your cell phone. That would be a pretty silly idea. And so there's always going to be use cases where we need higher resolution data where that's not present on a local device. So we're going to call out, and in this case, this is going to be a two-box architecture. We're going to call out to the edge for that. And that's running some sort of service that can respond with graphics. And that service then has an important decision to make. Well, first it has to check to see if the data is in cache locally. And if not, it has to make sure the cache is hydrated. How that cache gets hydrated isn't super important for this example. So assuming that data is resident, what do? Do we send the procedural instructions? Do we send the grammar back to the user, back to the endpoint device, and then run that generation locally? Or do we run that generation step on the edge and send the generated model to the user? So for one, we're introducing runtime compute at the edge. For the other, we're exchanging that for network bandwidth. And the answer is, you can do either. And there's different use cases for doing either. Let's say you've got 3 users that are geolocated within each other and in some sort of shared immersive experience. And so therefore, they're requesting the same tiles repeatedly. In that case, your code can determine that it's getting cache hits, getting very frequent cache hits for the same data. It probably makes sense to generate it once on the edge and not have to run that generation 10 times very frequently and send the actual data itself to the user. Maybe the user is running a very powerful device and you can measure that through some sort of empirical data. In that case, maybe it makes sense to send the grammars to the user and not cache the generated output on the edge. There's a lot of different cases for this, and you might want to actually make a programmatic runtime decision to decide which scheduling case makes the most sense. But the end result is the same. Either we send the generated model to the user, or we send the grammar to the user, generate the model. Either way, it gets uploaded to that device's GPU. And then you see an output that looks something like that, and the whole process starts all over again. So there's no right or wrong answer as to where to run your code, but what's important is the generation for this is written in WebAssembly. It can run on a Wasm time-based runtime wherever that can live, be it on the edge, be it on the client, be it on the server. Last example. This is also interesting because this is a very hot architectural topic these days. How to do machine learning inferencing on the edge. This is a very important topic for a lot of applications. And in this case, I'm going to use the example of user impressions. So let's say a user does a thing in a browser, doesn't really matter what kind of client, and you want to personalize that user's experience based off of some data that we know about the user. So instead of sending that data all the way back to your data center, identify who that user is based off of the metrics that are passed in from the client and personalize that experience. You can look up that profile and run that inference model. I thought I had Outlook stopped. I apologize for that. You can run that inference model at the edge instead, and this is becoming a pretty common pattern. And so you'd send those results, that personalization step, back to the user for immediate use after running the inferencing on the edge, and then you'd pass it back to the data center to allow further training or further processing of that data. Let's describe this system in terms of capabilities. As a user, you do a thing. Doesn't really matter what the thing is. Really? It hits the ingress for the edge, and you got a profile service that's just looking up to see if I have data in the edge cache, if I have information. If you do, it can connect the user to their model, and it can run that inferencing model using tools from Wasm on the edge. If it's not in the cache, that's fine. We can asynchronously, well, in this case, somewhat synchronously, still communicate with the data center, run that same profile service written in WebAssembly, running in the backend in Kubernetes as well. You can run that same profile service, but hook it up to a database instead. In that case, you can then hydrate the cache in the edge, send the data back to the user. So, this is kind of the classic case for caching. But the idea is to get as much of the information to the edge node as possible and still utilizing the backend capabilities. Could be for further retraining. Data scientists seem to always tweak their models. There's always going to be updates to the model as well. We still have a need for that data center, but we're able to write chunks of code and write modules that run regardless of the underlying host architecture, speed up the overall application, maybe even reducing cost as well. This gives a high-performance user experience, increases the flexibility of the code to run in the place that makes the most sense given that data locality. So 3 examples. Maybe they've resonated with people, maybe not, depending on your architectural and your systems. But as an architect, as a developer, you probably have a lot of questions like, where do I run my thing? My first answer is build the code for run anywhere. Build the code for WebAssembly by default. You will probably pay a higher price for doing that, especially in certain languages, than you might for just deploying it in a container or deploying it native. I'm not here to claim that you're automatically going to be able to build everything for WebAssembly and it's going to work super well the first time. But pay that slightly higher price, get it working in WebAssembly, test it, and make sure you have the capabilities to run it everywhere first. Utilize WASI, utilize some of the upcoming WASI cloud capabilities to unlock being able to run it in different locations at runtime. Consider what matters most to your business. Are you optimizing for total cost? Are you optimizing for user experience? Do you need fail-safe levels of reliability? There's no right or wrong answers here. It's all about what matters to the application itself. And then consider not just the cost, but the cost of performance when you need those additional levels. Sometimes you'll pay a financial premium in order to have a better user experience. Sometimes you can tolerate a slightly degraded experience in order to keep your product margins. And these kinds of decisions lead us to kind of 3 different categories or buckets. The cheapest way to run things, obviously, is to run it side by side with your data, so there's no latency. You can run totally distributed compute based off of lowest latency as well. That's an extreme example. Completely private networks, not going over public internet at all. Those are going to be the cheapest and the fastest way to do things. So how many applications can squarely fit in that green box? Probably very few things of actual substance. There's other options as well, right? Do I exchange some of that cheap compute for runtime compute? And by runtime, I mean online. I mean at an edge or a cloud provider. Can I use methods that reduce latency? Can I shop around for the cheapest egress? Can I shift compute around? Sometimes you need heavier capabilities. Database to edge replication is a cost and is expensive. And as outlined earlier, if you are moving everything from your database to edge, does the edge really make sense? Does it really provide that much value? Maybe, maybe not. I personally don't think so. If you're running a batch process though, right, maybe round trip latency doesn't matter, right? And so that's a good example of I'm doing asynchronous offline processing and exchanging that runtime cost. I think this is just kind of a heuristic framework for how people should be thinking about where to run their code. Nothing's going to squarely fall in one of these boxes, but for this application, pick out the individual items that matter to you. And lastly, this leads us to the concept of dynamic scheduling. Some of what I just described is necessary at design time, but I think the real power of WebAssembly is unleashed by shipping your code everywhere. By building for WebAssembly by default, abstracting away your dependencies through WASI Cloud, and being able to ship your code to all these different form factors, which is going to enable you to make some of these decisions automatically. Shift that compute around dynamically at runtime, depending upon metrics and measured weights. These weights can be set for what matters to your business, and so things like execution time. You can run high resolution timers, and you can measure things. You can say, here's the performance of this device as measured in real time. You can measure ping, you can measure latency. I'm sure everyone here has played a game where it starts lagging and then it gets better when the runtime switches you to a different multiplayer server. You can do these same techniques within your code as well, but you have to weight it according to your application's business metrics. Some costs can be measured, and then I want to leave with this. I think a dynamic scheduling framework can be built. This is a minimization problem. This is a basic set of components I would consider. You can use your own components. This is not just designed to be an exhaustive list, but some of the factors I've seen that are common across application architectures. Let's say device CPU. I define this as the sum of the CPU nanoseconds times that weighted business cost. Like I said, for real-time applications, every nanosecond counts. So you're going to want to assign a higher cost to that. Your edge cost, which I define as the sum of your resources running on the edge times whatever rate that edge provider is charging you, times your edge accuracy, which really this should be inverse edge accuracy. But essentially, what is your hit rate on your cache and your edge? Do you need to go back to the data center every time? If so, adding the edge is infinitely more expensive. Your storage cost, which is your storage weight times your bytes and whatever rate you're paying for that, plus any cost of replication. If you're duplicating data in multiple environments, you've got multiple data charges. While subtracting any deduplicated data. Maybe you can move it from the back end to the edge and it stays in the edge, and it's data that isn't necessary to keep in cold storage, for an example. Latency, which is just the sum of your providers. I say latency plus a factor because some types of latency are better than others. Some are built in. Like if you need to communicate to a database on localhost, always, that is a very defined factor, and that is something that you're always going to have to do. And so maybe you don't want to factor that into your application, but maybe if you're moving compute, I need to pull something from a data center in China while I'm here in New York, well, that's going to be an extremely expensive factor. And so we want to weight that heavier. I call this Kubernetes compute. Really, this is just your data center compute. But like I said, I think probably everyone's running Kubernetes at this point. The sum of your resources plus the overhead. Remember our compute graph shape? We're mapping client services to backing nodes times the inverse of that edge accuracy. Yeah, so I guess I got it right here. So whatever the remaining is from between your edge and your backend compute, that's going to factor higher on your backend. And then last, obviously, the egress cost, which I define as the weight times the sum of across your different providers, across every single hop, the sum of your bytes times your rate. That's luckily a pretty easy one to measure and define. And this results in the cost of performance. You want to minimize this cost. This is not intended to be an exhaustive list. You can define your own resources. These are what works for us. All right, so this takes us back to our original thesis, original topic of the talk. What is WebAssembly, what is universal compute good for? We've defined universal compute as using WebAssembly to write your code once and run it everywhere on a plethora of form factors. You can bring your code closer to where the data lives. Maybe the data that's important is on the back end. Maybe it's on the user side and you want to shift that compute around to match the cardinality of your data. You've got to make sure that the data itself, when you do have it resident, you have to move your code closest to that use case for the data, which is often where your user is. And through techniques like edge caching, you can minimize that cost. So build your code for WebAssembly. It's the enabler of being able to run your code without assuming a runtime environment through tools like Wasm and Wasm Cloud. Outsource your scheduling decisions to a minimum set of heuristics that matter to your application, and consider actually writing code that allows you to pick the best path and the best runtime environment itself. I think the future for WebAssembly as a compute engine is extremely bright, and I'm excited about all the possibilities that universal compute is going to bring to drive down costs, increase performance, and give us the best user experience for the next set and next generation of applications. That's it. Thank you.